All right, so for this one here, we get 8.8 grams of carbon dioxide. For this one here, we go from grams of oxygen to moles of oxygen. And from moles of oxygen gas to moles of carbon dioxide. Then from moles of carbon dioxide to grams of carbon dioxide. So again, there's 44 grams for every mole of that. The relationship between carbon dioxide and oxygen, 2 carbon dioxides for every 3 oxygens. See how we see that up here in the equation? So it's 2 of these for every 3 of these. All right, and then there's 32 grams for every 1 mole of oxygen. All right? So, under those conditions, okay? So, from this we can see that this is going to run out. It's only going to give us 8.8 grams, and this will be in excess. So our limiting reagent here is going to govern how much carbon dioxide we're going to get. So 8.8 grams of carbon dioxide is what we'd expect. Now, it said we got how much? 6.12. We got 6.12. So to get our percent yield, we take our 6.12, which is our actual, divided by 8.8, and then multiply by 100. So it looks like we get 69.6% about. So it looks like E is probably our answer. So this should be about 69. I'm getting about 69.5%. So it looks like E is our answer. Okay? Very good. So that's how we identify what the percent yield is. We take our actual yield over our theoretical yield. Okay? So that allows us to finish chapter 4 there. So now we're going to turn our attention to chapter 5. All right, so in chapter 5, we're going to talk about reactions that occur in aqueous solutions. Now, a lot of chemistry occurs in water, and that's what aqueous means. It means our chemicals are dissolved in water, and then they find each other in that aqueous solution, and then they react. If you're in an aqueous solution, it's easier for you to find your neighbors, right? If you're just a pile of A, and you're trying to react with a pile of B, then it's going to be hard because, first of all, you're not right next to each other. When you do get poured on each other, your big, relatively large chunks, crystals of material, some of the stuff that's inside those crystals aren't going to interact with each other. All right? So solids interacting with solids is sometimes trouble. But if I take A and make it aqueous, which means put it into some water, and dissolve it in the water, right? So here, now I have A dissolved in water, aqueous, and then I take B and do the same thing, dissolve it in water as well. Then I'll be able to react these very easily simply by putting them both into a container. And now my chemicals, which are both dissolved in water, they have the ability to move around and interact with each other easily. All right, so that's what chemistry under aqueous conditions means. Okay, now to start talking off here, we're talking about this, we need to define some definitions. We need to define some vocabulary. A solution is a mixture. It's a mixture of 2 different things, at least, sometimes more than 2 different things. And in that mixture, everything is homogeneously mixed. Or in other words, you don't have layers. If it's layers, it's not really a solution. It's not really a mixture either. The things aren't mixing. So a homogeneous mixture is when we have what we call when we have a solution. Now, an example of this can be, for example, a solution of water with salt dissolved in it, sodium chloride. And we can put a little aqueous sign there to show that it's dissolved in it. Okay, so when salt is dissolved in water, that is an example of an aqueous solution. We can also define the different parts of this solution. Our water we call our solvent because it's in the highest concentration. Most of this stuff in that mixture is the water, so we call it the solvent. And you guys have probably heard of that word. The solute is the chemical in the mixture that's in the lower concentration, and it's possible to have multiple solutes in a mixture. All right. The concentration of the solute is how many grams or how many moles or whatever it is divided by the amount of total solution. So one way of expressing concentration is what we call molarity. Molarity is the moles of solute divided by the liters of solution. All right. So, for example, if I have 1 liter of mixed solution here, right, and in there I have 0.2 moles of sodium chloride, then I would say moles of sodium chloride, 0.2 moles of sodium chloride for every, we said it was 1 liter. So this solution is 0.2, and big M is how you represent molar. So if a solution is moles per liter, we can say big M, it's 0.2 molar. Molarity refers to, again, the moles of solute for every liter of solution. Another way to express concentration is what we call percent concentration. Percent means out of 100, right? So when you're talking about percent concentration, you're talking about grams of solute for every 100 grams of solution. All right? That's an example of percent concentration. Grams of solute for every 100 grams of solution. Okay, so another word that we probably are already familiar with, maybe not though, we want to become more familiar with, is the word dilute. Dilute. A dilute solution means there's only a little bit of solute compared to the solvent or the solution. A concentrated solution means that there's lots of solute and that there's so much, if you were to add any more, it wouldn't dissolve anymore. And you guys have probably seen that before. If you add a lot of salt to water, the water will get saltier and saltier, but then it comes a point where it won't get any more saltier because all the salt you add, right, just goes and starts to form a pile on the bottom. So if I have some water here, and at first I add some sodium chloride, and the sodium chloride dissolves, right? But then after a while, the sodium chloride just begins to collect on the bottom and it stops dissolving. We say then that the sodium chloride, the solution is concentrated with sodium chloride. We can't get any more in it. Or that it's saturated. Another way of saying that, saturated. So saturation refers to how much of the solute there is. Solubility refers to how much can dissolve. Unsaturated means more can dissolve. And supersaturated, actually a condition where you can heat up the solution and dissolve more than you were theoretically supposed to be able to. I don't know if any of you have ever tried to make syrup. You can make syrup by putting sugar and water, but you actually add twice as much sugar than you do water, which isn't enough water to dissolve all that sugar. But what happens is, as you heat it up, the solubility of the sugar changes, and so the sugar can finally dissolve as you heat it up. But then when it's cooled down again, you have what's called a saturated solution. Supersaturated, sorry. All right, so let's watch this video here. In this video, we have a solution here, and it is supersaturated. Now, it still looks aqueous, and it is, but as soon as it gets disturbed, even just the littlest amount, the precipitate will start coming out. And so we'll watch what happens. They disturb the surface just a tiny bit, and then as soon as that happens, you get the crystals. Whoops. Try it again. You get the crystals that begin to precipitate out right away until the whole thing eventually crystallizes or solidifies with solid of whatever the salt is. Okay? So that's an example of a supersaturated solution that is precipitating out its salt from inside. Again, we call this a precipitate when the solid comes out of the solution. All right. So if we're told the solubility of sodium chloride is 39 grams for every 100 grams of water at 100 degrees Celsius, and we dissolve 100 grams of salt in 50 grams of water at the same temperature, the question is this solution saturated, unsaturated, supersaturated, or none of these? All right, see if you can answer that one. See if you can answer that one. Take some time to see if you can answer it. Okay? Make sure you take time. All right, push pause if you're not done. But what we see is there's 39 grams of sodium chloride for every 100 grams of water in a regular solution. And they're now making a different solution of 10 grams of sodium chloride for every 50 grams of water. And we want to know, is this solution going to be saturated, unsaturated, supersaturated? Well, half of 39, because we used half as much water, so we should be able to dissolve half as much sodium chloride. So 39 divided by 2, that's 19.5. We should be able to dissolve 19.5 grams of sodium chloride. And we only have 10 in there. So this solution is going to be unsaturated. All right? It's not going to be saturated. There's more salt that can be dissolved there. Okay? Now, I don't know if you remember, but we talked about ionic compounds existing as what we call three-dimensional lattices. Three-dimensional lattices. A three-dimensional lattice is a repeating, again, dimensional shape of our ions. So, let me
sodium chloride crystals are held together by attractive
forces.
turn down the video here for a second.
Sodium
But
and negatively charged.
this here is an example of our three-dimensional lattice. We have repeating units of sodiums and chlorines all packed together in this crystal. All right, it's a repeating three-dimensional lattice of ions. Now, that's how a ionic compound is found. But when you drop this compound in water, when you drop an ionic compound in water, then something happens. Okay? So let's watch this video and watch what happens.
When a crystal
Well, we already know that the salt will dissolve, and we want to know how that's happening. Well, as you can see here, this is a chloride ion, the green one. The water molecules are surrounding the chloride ion, and they're convincing the chloride ion to leave by satisfying that negative charge that's on that chloride. And then same thing happens here. The oxygen end of water molecules surround the sodium ions, and they slowly separate apart. And over time, all we have is sodium ions and chloride ions floating around surrounded by water molecules. So it was this three-dimensional lattice, but once you put it into water, they'll dissolve. Okay? So, ionic compounds in water, if they're soluble, if they can dissolve, will always be ions. Always be ions. Okay? So, for example, if I have sodium chloride and it's in water, another way that I should think about that is, and I take this thing and I split it up into its ions. Those are the ions, right? Now I have to remember how I know that this is an ionic compound. I can tell it's an ionic compound because I have a periodic table, and on my periodic table I see that this is a metal, sodium, and a non-metal, So this is an ionic compound. All right. So I have an ionic compound put into water. It will just separate into its ions. Okay. So ionic compounds dissolved in water don't go around in little packets of sodium chloride. They go around as ions, sodium ions and chloride ions. And we should put aqueous on there to remind ourselves that they're aqueous. Molecular compounds can also dissolve in water. Molecular compounds can dissolve in water, but when they're dissolved, they don't go around as little ions. Right? So, for example, if we have something like PCl3, PCl3 is a molecular compound. We can tell that because looking at our periodic table, all right, we see that phosphorus is a nonmetal and chlorine is a nonmetal. Okay, so we have PCl3. It's it's a molecular compound. Therefore, that means it's not going to dissolve in water. It's not going to dissolve. Well, sorry, it is going to dissolve, but it's not going to ionize in water. So we could still get something like this, which is solid, going into PCl3 aqueous, right? But we're not going to get PCl3 to ionize. Right? It's not going to ionize because it's not an ionic compound, right? Okay. So, what we'd like from you is to be able to see that you can look at these compounds, these ionic compounds, and separate them into their ions and also identify the number of ions that there are and the charge that's on those ions. Okay? So we start off with Na3PO4. This is an ionic compound made of two different ions, so I'm going to write those ions down. We're going to show this compound dissociating into sodium ions. Now, how did I know there was a +1? Well, I have to look on the back of my periodic table here and find out what the PO4 3- ion is. It's right here. It's the phosphate ion, PO4 3-. Therefore, if this is a PO4 3-, and I can write that over here while I'm at it, I must have a +1 to need 3 of these sodiums. I also have to write down the 3 there to show that there's 3 sodium ions. I can also write in here, if I'd like, the aqueous to remind us of the aqueous. But in general, that's how you write what's called the dissociation equation for an ionic compound. Ionic compounds will ionize, and upon ionization, they also dissociate, form the dissociative products of this compound. Okay? Very good. Why don't you try the next 3, and we'll see how it goes.